Alright, so let us get started. So, this is week 3 of problem solving sessions for the course on fluid dynamics and turbomachines. As we all know, this course is being offered by NPTEL and it's being instructed by Professor Shamit Bakshi and Professor Dhiman Chatterjee from the Department of Mechanical Engineering at IIT Madras. I am Debjit. I am a PhD scholar at IIT Madras and I am the TA for this course. And like every other week, we shall be solving some problems together. So, week 3 has been on the differential analysis of fluid flows, and in more detail, we got to learn about the continuity equation, the momentum equations or the Navier-Stokes equations. Then we learned about Euler's equation and Bernoulli's equation and how to derive them and also how to use them. So, and we also learned a bit about stream function, potential, velocity potential function, as well as its uses in analyzing fluid flow. And we also learned a little bit about how these equations change if the flows are steady versus unsteady or incompressible versus compressible and so on. So these will all be useful as we move forward and start learning about turbo machines in the next module of the course. So, without any further ado, let's get started with today's session. So, it's a very simple question to start with. Question number 1, which is asking us that which of the following equations, there are 4 equations given in the options below. So, which of the following equations is the most general form of the continuity equation for a fluid flow? Not just for a fluid, for a fluid flow. So, the main key word over here, that is most general form. So there are different forms of the continuity equation as we learned. Which one is most general? Which one can be applied to the widest variety of fluid flow scenarios? Is it option A, dou rho dou t plus the dot product, or sorry, the grad of rho v vector, or is it option B, uh, dou u dou x plus dou v dou y equals 0? Or is it option C, grad of v vector is equal to 0? Or is it option D, the dou p dou t plus dou v dou x equal to 0? So I beg your pardon, this is not grad, but this operator is the divergence operator. So where we do nabla dot, so nabla is a vector over here which just represents I cap dou x plus j cap dou y plus k cap dou z. So this is the divergence operator which operates on the vector inside it. So the first option is dou rho dou t plus divergence of rho v vector equals 0. Option B, dou u dou x plus dou v dou y is equal to 0. Option C, the divergence of vector v equal to 0. Or is it option D, dou p dou t plus dou v dou x is equal to 0? Let's take a look at the solution. It's actually option A, dou rho dou t plus divergence of uh, rho v vector equal to 0. This is the most general form which can be applied for, unsteady compressible flows. If the fluid flow is either steady or incompressible, then this form can be simplified down. And if it is, and this is in 3D, this particular equation, if the flow situation can be boiled down to a 2D or a 1D scenario, then that equation gets even more simplified. So this is the vector notation of this equation. So if we expand it out and write in the scalar form, then this simply becomes rho x rho u, where u is the x component of velocity, u, v, w are the three components of velocity in the x, y, and z coordinates. So dou y of rho v plus dou z of rho w equals 0. This is the expanded scalar form of this equation. and it's the most general form of the continuity equation for a fluid. Alright, so moving on to the next question, which is asking us. So, once again, in continuation of question number 1, if we simplify that continuity equation and we can write that as the divergence of velocity equal to 0, under what conditions can it be applied? Is it when it's option A, steady compressible, sorry, option B, unsteady compressible, option C, steady or unsteady incompressible, or is it option D, none of the above? So let's take a look at the solution. It's actually option C, but let's go through the other options. So, as we discussed in the earlier slide, so the most general form for the unsteady compressible flow is this one, dou rho dou t plus the divergence of rho v vector equals 0. Now, if it becomes steady compressible, then only this part will go to 0. And the steady compressible version of the continuity equation will be rho v vector equal to 0. So, since it's compressible, rho is a function of x, y, and z, the spatial coordinates, but since it's steady, it's not a, it's just not a function of time. Now, if it's incompressible, then rho becomes a constant. Then dou rho dou t goes to 0, as well as I can take this rho out and I can simply write the divergence of velocity equal to 0, and this rho cancels out because since it's equal to 0 on the right hand side. So it really simplifies down to this equation, whether it's steady or unsteady, just because if it's incompressible. So that's why option C should be the correct answer. Okay, so let's move along. We will be yeah. Okay, so let's move along to the next question, which is question number 3 of today's session, which is asking us that the Navier-Stokes equations represent which fundamental law? Is it option A, conservation of energy? Is it option B, conservation of mass? Is it option C, conservation of momentum? Or is it option D, the Newton's law of cooling? So there is a fundamental law of nature that we know, which is represented by the Navier-Stokes equations in the Eulerian frame of reference. So in the first week of lectures, we learned about the Reynolds transport theorem, which lets us apply the system level fundamental laws of nature that we know to control volumes. So it lets us to transform from a Lagrangian sense to an Eulerian sense, an Eulerian frame of reference. Now, Navier-Stokes equations is the Eulerian frame of reference or the control volume version of some fundamental law. Which law is that? Is it option A, the conservation of energy? Is it option B, conservation of mass? Is it option C, conservation of momentum? Or is it option D, Newton's law of cooling? Let's take a look at the solution. It's actually conservation of momentum. So the continuity equation is the conservation of mass, and the conservation of momentum is the Navier-Stokes equations as we know it, which balances the momentum being stored in a control volume, either increased or decreased, with the amount of momentum transported in or out of that control volume, with the forces applied on that control volume. So it's the conservation of momentum in the Eulerian frame of reference. That's known as the Navier-Stokes equations. And the fundamental law that it represents is conservation of momentum. Alright, hope that's clear. We will move along. We will move on to question number 4, which is asking us that in a two-dimensional incompressible steady flow, the existence of a stream function psi, that we a single one over here, just single psi, implies what? Is it that option A, the flow is irrotational? Is it option B, the continuity equation is automatically satisfied? Is it option C, the flow is always steady? Or is it option D, that the velocity potential must exist? So, focus on the question. So it's given that it's a 2D incompressible as well as steady flow. Given that if there is the existence of a stream function psi, what does it imply? Does it imply that the flow is irrotational? Does it imply that the continuity equation is automatically satisfied? Uh, does it imply that the flow always has to be steady and it won't be, you know, this also implies that in case it's unsteady, then the stream function won't exist? Or is it option D, that simply the existence of stream function guarantees that a velocity potential must also exist? Alright, so let's take a quick look at the solution. It's actually option B, that the continuity equation is automatically satisfied. So let's go through the other options and see why they're wrong. So option A, the flow is, option A, that the flow is irrotational. It doesn't has to be. Rotational flows can have psi. The existence of psi can be there. The third one, the flow is always steady, also something that doesn't have to be true. Even there could be a stream function which is not only a function of space but a function of time as well. It can represent unsteady flows. And option D, this is connected to option A, saying that since stream functions can be defined for an irrotational flow, uh, in that case, velocity potential won't exist because velocity potential can only exist in case of irrotational flows only. For rotational flows, they cannot exist. So that's why all these three are incorrect options. And if we look at the definition of psi, so psi can be defined as dou v dou x, or it's the other way around. U can be represented as dou psi dou y, and v can be written as minus dou psi dou x. So if we go back to the continuity equation, that dou u dou x plus dou v dou y equals 0. This is the continuity equation for a steady incompressible flow. And if I plug in these two values, so then what I get is dou 2 psi dou x dou y minus dou 2 psi dou x dou y equals 0, and it is automatically satisfied. So this is the benefit of using stream function, that simply by definition it satisfies the continuity equation. Then on the next step you can try to solve for the actual flow fields by plugging this into the uh, momentum conservation equations along with suitable boundary conditions. So that reduces, so first of all you can see that instead of u and v, it boils down to only a single variable psi. So the number of variables get reduced. Also, we can eliminate the continuity equation, which we don't have to worry about anymore since it automatically satisfies it. So the number of equations also come so that number of equations also comes down. So it simplifies problems in many contexts. Anyway, so that was question number 4 after a session. Let's move on to question number 5, which is asking us that which of the following statements is true about velocity potential function phi in fluid mechanics? Is it option A, that it exists only for rotational flows? Option B, that it exists only for irrotational flows? Option C, that it exists for any two-dimensional flow? Or option D, it is defined only for incompressible flows? Okay, so let's take a look at the solution. It's actually option B. It exists only for irrotational flows. So that's how phi is. So the definition of phi is that u is dou phi dou x and v equals dou phi dou y, and it is only defined for irrotational flows when for irrotational 2D flows, we can write this as dou v dou x minus dou u dou y, that is the vorticity in the z direction, equals 0. Then only if I now plug in these two values of u and v, we get the rho 2 phi dou x dou y, the mixed derivative of phi being subtracted from itself being equal to 0. Only then is it satisfied. If the flow has some finite value of rotation, then this equation is not satisfied and we cannot define a velocity potential function phi in that case. Oh, sorry. So it exists only for irrotational flows. Okay. Hoping that's clear. Let's move on. We'll move on to sorry. We will move on to question number 6, which says that for a flow field that is irrotational as well as incompressible, which partial differential equation must the velocity potential phi satisfy? Is it option A, the Poisson's equation? Is it option B, the Navier-Stokes equation? Is it option C, the Laplace's equation? Or is it option D, the Bernoulli's equation? So these are two key words. Let's say the flow is irrotational as well as incompressible. In that case, which partial differential equation must the velocity potential phi satisfy? Is it option A, Poisson's equation? Option B, Navier-Stokes equation? Option C, Laplace's equation? Or is it option D, Bernoulli's equation? Let's take a look at the solution. It's actually option C, Laplace's equation. So we will go through this. So first of all, irrotationality is a requirement for phi to be defined in the first place, and if it is incompressible, then the continuity equation can be written like this: dou u dou x plus dou v dou y equals 0. And once again, let's revise the definition of phi, that is u equals dou phi dou x, v equals dou phi dou y. So we plug that into this equation, and what we get is dou 2 phi dou x square plus dou 2 phi dou y square. This is in 2D. If this was 3D, then dou 2 phi dou z square would also exist. And the sum total of them is equal to 0. So, in a general sense, this can be written as Laplace square phi. The Laplace square operator is also known as the Laplacian operator. It simply means dou 2 dou x2 plus dou 2 dou y2 plus dou 2 dou z2 being operated on something. Uh, this is the Nabla square operator. So this implies that the Laplacian of phi is equal to 0, and this equation is known as the Laplace's equation for any given variable. So in this case, the variable is velocity potential and it has to satisfy the Laplace's equation. Now the neat thing here is that, if you do have an irrotational and incompressible flow field and you know the boundary conditions, then solving for this Laplace's equation is actually very easy and straightforward, because this is such a common equation that there has been a lot of work being done on it, and there are many different ways to efficiently solve this equation, given that you know the boundary conditions and it's a well posed problem. So all this leads to a very easy solution for the phi, and once you know the phi, you can get the velocity field and visualize the velocity field, visualize the flow physics very nicely. So this is another advantage of defining the velocity potential phi in cases where it can be defined, and then analyzing the fluid flow using it. Okay, so let's move on. We will move on to question number 7. Now, this is interesting. We have two figures over here with two sets of equations given below. These equations are the flow field equations, and the flow fields you can see in the figures above. The question is, you have to identify which of these two flow fields are incompressible. Is it just one? Is it uh, just two? Or both? Or none of the above? So let's try checking it. So we will start with sorry. Let's start with number 1. So U and V are given, and the way to test incompressibility in a 2D flow field is to see if the velocity field satisfies this equation, dou u dou x plus dou v dou y equals 0. So u is 1 minus x squared plus y. So the x derivative of it would be minus 2x plus dou v dou y. So v is 1 plus x minus 2xy, and deriving it by y should give me minus 2x. So this is equal to minus 4x, and it does not satisfy the uh, incompressibility condition. Now let's take a look at number 2. So once again we will do the same thing. Dou u dou x plus dou v dou y. We will test it out. So dou u dou x, in this case, u is 3y squared plus 2x. So its derivative with respect to x should be 2. And the derivative of v with respect to y, v is minus 2y plus 3x squared. So it should be minus 2. And 2 minus 2 very simply is 0. So the second one satisfies the incompressibility condition. So this flow is incompressible, whereas the first one is not. Okay. So this is a very simple way to test the incompressibility given that you know the flow field. Plug in the values, compute the derivatives, and then see if it satisfies the equation or not. Alright, so moving on. So it's the same set of equations once again. The question is different. If now it's asking whether these are irrotational or not. So once again we will follow a similar procedure. So the condition for irrotationality is that omega z is equal to 0, and omega z is equal to dou v dou x minus dou u dou y is equal to 0. So let's plug the values in. V in this case is 1 plus x minus 2xy. So its derivative with respect to x is 1 minus 2y, and the derivative of u, which is 1 minus x square plus y, is plus 1. So this is equal to minus 2y, which is not equal to 0. So this is not irrotational as well. This is rotational flow. Now coming to the second equation, second flow field. So once again the condition we test is the same, dou v dou x minus dou v dou y. Is it equal to 0 or not? So v in this case is minus 2y plus 3x squared. So if we derive it with respect to x, we get 6x minus dou u dou y. U is 3y squared plus 2x, and deriving it with respect to y gives us 6y. And once again, this is not equal to 0 in general. So once again, this is also not irrotational. So your answer should be none of the above. Both 1 and 2, the flow fields, are in fact rotational. There is a finite vorticity everywhere. Okay, so let's move on. Let's move on to question number 9. Okay, so this is a numerical type question which is telling us that a gas flows from a large reservoir at gauge pressure P. So this will be important. At gauge pressure P, through a pipe that rises vertically to a height h and emerges as a free jet. So let's draw the picture that it is painting. So I have a large reservoir filled with gas, and there is a pipe which rises to some height h. So this height is h, and the gas is being ejected as a free jet out of this pipe. And this inside is at a gauge pressure P. Gauge pressure P meaning that it is P units of pressure higher than the atmospheric pressure. This outside is at P ATM and this is at P plus P ATM. We can simply subtract the atmospheric pressure from both ends and consider 0 outside and gauge pressure P inside. And if you assume that the flow is inviscid, the flow is incompressible as well as steady, and you neglect friction. So, being inviscid and neglecting friction is the same thing. And you apply Bernoulli's equation between the reservoir and the free jet. You have to derive an expression for that exit velocity v of the jet as a function of h. So another important piece is that, let's say the density of the gas is rho, and since it's incompressible, it's rho inside as well as outside. So applying Bernoulli's equation, so let's fix 2 points. Let's fix one point inside the reservoir, and let's fix another point just at the outlet of the exit. So now let's apply Bernoulli's equation. Bernoulli's equation says that P1 plus rho v squared by 2 plus rho g h should be equal to, result 1 should be equal to P2 plus rho v2 squared by 2 plus rho g h2. Now at 2 this is h, and at 1 let's say this is 0, and h2 is equal to h. V2 is something that we have to find. Let's say V2 is equal to this velocity V over here. V1 is also 0 since the gas within the reservoir is at rest. P1 is equal to this gauge pressure P. So this is small p, and P2 is 0. It's actually the atmospheric pressure which are subtracting to get the gauge pressure in the first place. So ultimately this boils down to small p, gauge pressure P is equal to rho V. I'll write this as just V now. V square by 2 plus rho GH. And if I solve for V, that should be P minus rho GH. This has to be divided by rho, has to be multiplied by 2, and this whole thing has to be taken as square root of. So this is an expression of the exit velocity of the gas jet V as a function of the pressure, the gauge pressure inside, as well as the height at which the free jet comes out. Okay, so let's move on to last question of today's session. Sorry, it's a bit stuck. Let me fix it once. So this is question number 10 of today's session. So a velocity field is given. So u and v are known as functions of x and y. What is the correct expression of the vorticity or this velocity field? Is it option A, 2x squared? Is it option B, 3x squared? Is it option C, just x squared? Or is it option D, x cubed? Okay. So very simply we will compute the vorticity, which is given by dou v dou x minus dou u dou y. So, if you can't remember this, the right, correct way of finding the three-dimensional vorticity field is this way. You take the determinant of, first of all, ijk, then the derivatives dou dou x, dou dou y, dou dou z, and the velocity components u, v, w. So this basically comes out of the fact that the vorticity field is the curl of the velocity field. So, however you write this. So, okay, maybe I should move down a bit. So the vorticity is expressed as the curl of the velocity, capital. I kept making the same mistake. But anyway, so in this case, we are only interested in the z component of vorticity, and as you know, so there it has to be calculated this way. So the product of this, so dou v dou x minus the product of this, dou u dou y. Okay, so now let's plug in the values of u and v, which we know are 2x square y and x cube. So basically dou x of 2x squared y, so no, dou x of x cube, which is v, minus dou y of u, which is 2x squared, 2x squared y, sorry. And if we do the derivative, then we get 3x squared minus, I have here 2x squared. So the difference should give me just x squared, which is option C. And let's take a look at the solution. It is indeed option C. So that's all for this week. Thank you.